Okay, now we got a question. We got a system. The total pipe length is given. The oil tank for the hydraulic system is given in the figure. The pressurized, it is pressurized, so 68 kilopascal. So the pressure is 68 kilopascal. At gauge pressure, so that's gauge pressure. The inlet to the pump is 3 meters below the oil level. So the inlet to the pump is the oil level, and that one is 3 meters. The pump flow rate is 0.001896. The flow rate is given as 0.001896 meter cube per second. We need to find out the pressure that's at this point. Now the total length is 6 meters. We also given the specific gravity of the oil is 0.9. We also given a kinematic viscosity as 100 centistoke. Now centistoke is a unit for the viscosity. Assume the pressure drop is around 6.9 kilopascal, and the total length and the pipe diameter is given as well. Total length is 6, and the pipe diameter is 38 millimeters. That's the diameter of the pipe. That's the total length. Kinematic viscosity. That's the pressure. This is the pressure that is lost here. Yeah, the pressure dropped 6.9 kilopascal. No, that's not in kilopascal. Yeah, this is in kilopascal. So we need to find out the pressure that's at that point. Okay, so first we do is we write down the equation. Okay, now this is the Bernoulli's equation we are going to use. The Bernoulli's equation says like energy at point 2 should be same as energy at point 2. So there is no loss of the energy. Total energy remain constant. So this is form of the Bernoulli's equation. Now, where Z1 or the Z1, Z2 is the difference between this height. So I got a Z1 and I got the Z2. So I can subtract them. Z1 minus Z2, that will be 3. So in this equation, you are given the Z1 minus Z2, which is the 3. Now we need to assume that the velocity here is going to be 0. Velocity at point 1 is going to be 0 because it is flowing at very low velocity. So velocity 1 is nearly equal to 0. The reason is because the diameter of this thing is a lot bigger than that diameter. So velocity that is going to decrease is very less, so that's nearly equal to 0. Now we can find out the velocity 2. To find out the velocity 2, we need an equation. Now continuity equation we need. So V2 is the one we need to find out. We know the flow rate is equal to the area, cross-sectional area, multiplied by the velocity. Now the flow rate, we know the flow rate here should be same as the flow rate in the pipe. So flow rate is same. So flow rate is given. We got the Q, which is 0.001896, and the area is pi r squared. So area of the pipe, pi r squared. The r is 30. So that's the half of that one, 19. But this is millimeter. So 10 to the minus 3 pi r squared. That will give me the velocity 2. So I can divide this one, 0.001896 divided by pi 19 times 10 to the minus 3. Make sure when you put that one, minus 3, and there should be a bracket here. Otherwise, you will get incorrect answer. That will give you the velocity 2. So let's find the velocity 2 first. Anyone got value for the velocity 2?
People 1.5 times 10 to the minus 6.
Now we got the velocity. So the thing that's missing is we already, if we look into this equation, I have this value. I have this value already. This value minus this value, I have the answer. So that's fine. pressure 1, I have the value for the pressure 1. I have the V1 that's given to me. 0, we assume. That's it. G is 9.8. Z2 minus Z1, we know. P2 is the one we're trying to find out. V2 is given. Now we need to also find out the HP, the motor head, pneumatic head, and we need to find out all these, the HL, all the values. Now what we're going to do is we need to calculate these bits. To do that, we already got the velocity V1 and V2 as 1.67 meter per second, and the V1 is 0. What we need to do is, now you need to find out, where's the equation? You need to find out that the value for this bit, V2 square over 2G. Let's find out the value for this bit, and let's do that one. So if I want to find that bit, let's do V2 square over 2G. That is going to be, V2 is how much? We already got the value. So try not to round it off. I know it was 1.67 something, but let's do that one. So square divided by 2 times 9.81. And if you can do that one, anyone got value, please? 0.14. Yes. 142. Yeah. Let me just drop that one. So that is 0.14142 meters. The unit of that one is going to be meters. Now we need to find out the head losses. So we have that bit. We done this bit. Now we need to find out the HL, the head losses. Now head losses is HL. Now this has an head loss. This has an equation. It's an equation. The equation is given by F. We talk about that one. Times L over dP multiplied by over 2G. Okay. This is the equation. We have the value for the LP. We have the value for the dP. We have the value for the V over 2G. We have these values. Yep, we can find that one. The thing that's we don't have is the friction coefficient. F is the friction coefficient factor. So let me write it down. So F here is a friction coefficient factor. Friction coefficient factors come from the Reynolds number. Now, Reynolds number is a number that actually is linked to flow, type of flow. If there's a turbulent flow, there is a Reynolds number. If there is a laminar flow, non-turbulent flow, there is another number, Reynolds number. So we need to find this bit. Now, to find the Reynolds number, first we need to find the Reynolds number, and then we can actually have a look at the friction factor. Okay, Reynolds number has a formula. Now, Reynolds number formula is viscosity, that one, over diameter of the pipe multiplied by the dynamic velocity. Okay. This is the value for the formula for the Reynolds number. I have the velocity 1.67. I have the diameter, which is 38 millimeter, and I have the value for the kinematic viscosity 100 centi-stroke, sorry, not centi. Just to give you an idea, if you want to convert that into a standard unit, you need to multiply by 10 to the minus 6, yeah, and that actually can convert into Pascal meter, yeah, because if it's centi-stroke, this is, we can convert into the standard unit. So let's put that one. Let's put this one. V2 is 1.67. Let's put that one here. 1.67. GP is 38 millimeter. So 38 times 10 to the, actually, that will become 0.038 divided by this thing, which is 100 times 10 to the minus 6. So that converts into that one. Anyone got a value for the Reynolds number?
634.6.
634.6. 634. Can you press the ENG button in your calculator? Oh no, 634.6. That's it. I thought, yeah, 634.6. Okay, that's it. Now this Reynolds number, if it's more than 2000, if the Reynolds number is more than 2000, it's a turbulent flow. If it's less than 2000, which is less than 2000, it is laminar flow. So this number is less than 2000. So the flow is laminar. Laminar flow means it's a smooth flow. So we got a laminar flow.
Wait, so Pascal meter the same as Newton meter squared?
Newton meter squared, no, a little bit different. We talk about the unit conversion later. Okay. Now what we got is we haven't got the friction factor. We haven't got the friction factors. Now we need to do is to find the F. To find the F, we have another formula. Now the formula is F equals something over Reynolds number. Now the formula is different for the turbulent flow. The formula is different for the laminar flow because it is laminar flow. So I'm going to use this formula. These will be given to you. F equals 64 over RE. So we just put the values. (64) divided by 634.6. Anyone got an answer for the F? 0.1. Okay. So F is 0.1. So I have the friction factor. Now I got the value for the F. I got the value for the F. I have LP and I have everything. So I can put that into this equation and get the value for the HL. So let's put that one in this equation. F is 0.1. LP is 6 meter. That was 1.67. Diameter of the pipe is 0.038. And the 2G, I can put either here or there, it doesn't matter. 2G is 2 times 9.8.
Wait, so we already just worked that out. We just worked out V2 V squared over 2G.
Oh yes, we already worked out V squared over 2G, so we can just put 0.142. Yeah, that's a lot easier. So we don't need to do that one. We can, instead of that one, we already have this value, 0.142. That's it. So that is going to give you the head loss. Anyone got an answer? 2.24. So we got the head loss 2.24 meters. Yes, units are going to be. Yeah. We need a bigger board. Okay. Okay, I'm just going to F is 0.1. Okay. Yeah, so we got F 0.1 and Reynolds number 634.6. Yep, so I should rub that one because that's here. Friction factor, Reynolds number, let's see the Reynolds number here. 2.24. That's head losses. It's 34 point. Okay. I got the answer. I got the head loss due to friction is 2.24. I also did that value V square over 2D as 0.14. I know Z1 minus Z2 is 3, so which is here. Now I need to do is I need to find out the next point, which is point Q, which is here, and I need to find out what's going on here. So I need to do is I need to find this P2 over gamma, and then we actually solve that bit. Okay, let's make this thing a subject, P2. So I'm just going to make this thing a subject. Rearrange the formula. V1, what's the value of V1? V1 is 0, so 0 divided by anything is a 0. So that thing is going to be 0. Okay, so let's rearrange the form. Yeah, that will multiply 8.32. You got 8.3. Yeah. So that is 8.32. Okay. So there's a recording in progress now. Yeah. Oh, okay. Yeah, you can do it backwards. Oh, I've been doing backwards. Did I?
Yeah. You've been recording when you've been wiping the board off.
Yeah.
Oh, okay.
You have recorded.
Okay, I will see.
Just random thing with it.
Yeah.
Good job, we're all clever. We love the study.
Okay. Did I mention that one? Yeah. Well, not good in uploading the video. Okay, so we got the Z1, Z2, which is 3, that one P1 over gamma. P1 is 68 kilopascal. HP minus H naught, because they are in the same level, so that's 0. There's no head loss. We find the HL 2.24. We got this value 0.142, which is from here. and that's equal to P2 over gamma. Then we put that in the equation straight away. We got P2 over gamma as 8.32. The gamma is specific viscosity times 9,800, and that will give us the pressure 2, which is 73.45 times 10 to the 3, and you can convert that into kilopascal.